In this video, we're going to look at another example of finding the volume of a solid using spherical coordinates. So we're being asked to find the volume of a smaller wedge cut from a sphere of radius a, where two planes intersect along a diameter at an angle of pi/6. Alright, so we're being told that we're looking at a wedge of a sphere of radius a. Well, if we're in that wedge, then we have to have our rows going between 0 and a. All right. So we've got a lot of latitude with how we can picture this thing, but probably the easiest way to picture it, at least in my mind, is to take the plane y equals 0, which would be the plane that's perpendicular to the xy plane that runs straight through the x-axis, and then rotate it 30 degrees from the positive x-axis, rotate it pi/6, and then you'll get the equation y equals √3/3x. So in this case, if I think about those two particular planes, this gives you your theta. It has to be between 0 and pi/6, going from the positive x-axis up to that other plane. Now again, we're saying that we're in the wedge of that sphere cut by those planes. Notice that doesn't restrict our z at all. It doesn't tell us that we're cut off by the xy plane or anything. So again, if we think about our phi rotating from the positive z-axis in downward towards the xy plane, phi can go all the way from the positive z-axis to the negative z-axis, or from 0 to pi. So finally, when we want to find the volume using a triple integral, we can just do the triple integral over the solid of the differential of v, dv. So when we do this replacement in spherical coordinates again, we replace the differential with rho squared sine phi d rho d theta d phi. The rho's are going from 0 to a, the thetas are going from 0 to pi/6, and the phi's are going from 0 to pi. And like I've mentioned in a couple previous videos, I've got an integrand that factors as a product of three single variable functions, and the constants my limits of integration are all constants here, so we can break up this iterated integral as the product of three integrals. So now we can evaluate each of the integrals individually and get a final answer of pi a cubed over 9.